Hello everyone, my name is Rafael Nieves and today I'll be presenting our project titled RPN Rocket for SECME, developed by me, Nicholas Polonsky, and Paula Bastardo. Now to begin, I'd like to show you guys a couple of pictures of us actually delving into our project. So here you can see us holding our final product, and here you can see me pumping air into the rocket. So why is this? Well, the functionality of the rocket to simulate a real rocket and real projectile motion actually uses a hand pump that I'm pumping right here in order to put air into the rocket's chamber so that it has pressure inside of it at some point, eventually allowing it to launch up into the air thanks to the buildup of pressure, thus launching it like a real rocket, simulating projectile motion. Now here you can actually see a video of that. So in the back, I'm pumping air into the rocket until eventually around 4 seconds before the video ends, the rocket is launched into the air and eventually falls back down after reaching a height maximum. Now, from this experiment, we could collect a little bit of raw data from that video you saw back there, as a matter of fact. And you can observe that it took the rocket around 4 seconds to complete an entire launching and landing cycle, and it reached a maximum height at around 2 seconds. Now note that this graph is mapping time to the vertical displacement of the rocket. That is how far it was from the ground at every single given point in time, from its launch to its eventual descent. And from this data, we were able to make some calculations using some important formulas, given mainly the rate of change formula, the acceleration formula, and the average velocity formula, which allowed us to get some important values: our acceleration, our average velocity, and most importantly, our initial and final velocities, which we're going to use mainly in our development of our mathematical model. You can see in this next slide over here. So as predicted before, this model for the movement of the rocket follows a parabolic movement. That is, it reaches a maximum and then after this it goes back down and hits the ground again. You can see that it simulates the rocket's motion very closely if you think about it. And it is actually given by this function over here, which uses our initial velocity as a coefficient of t and the Earth's natural deceleration as a coefficient of t squared to form a parabola, which models the motion of a rocket, and we can use to predict its position at any given point in time. Now from this, we can conclude two things. Mainly, regarding our rocket's design, given that this was for a competition, we could have made it better so that it stayed in the air longer and its parabolic motion was a little bit more widespread, rather than as collapsed as you saw in the previous slide. Parabola more like this one. So more flight time, higher amount of flight, and also a longer amount of time. A time span of longer flight would have made it way more competitive than it is right now. And as for the experiment itself and the discoveries that it allows us to make in regards to physics, any motion that a project realizes in nature is going to be parabolic if there's nothing else affecting it externally. Thank you very much. I hope you have an awesome day.